In this video, we're going to take a look at the topic of limiting reagents, part of reaction stoichiometry. I'll do a few of the questions from the set of worksheets, and then you'll have the remainder to do on your own. Throughout the video, it would be a good idea if you paused the video and tried the question yourself, and then just played to see if you were getting it correct. Question number 1. We have a reaction between aluminum sulfite, Al2SO3, and sodium hydroxide, NaOH. It looks to be a double replacement reaction. The products are aluminum hydroxide and sodium sulfite. We're asked if 10 grams of aluminum sulfite reacted with 10 grams of sodium hydroxide, which of those would be the limiting reagent? Now, the word reagent is almost synonymous with reactant. Okay, those are almost the same things. So the limiting reagent simply refers to which of these two reactants, we know we have 10 grams of each, limits the amount of product that we can make. If you think of it for a moment as perhaps baking cookies, if you were baking cookies, you could keep baking cookies, making more and more cookies, as long as you have all of the ingredients for your recipe. But once one of the ingredients runs out, you have to stop making that recipe, and so your cookie baking would stop. So the number of cookies would be based on the ingredient which ran out first while cooking. In the same way, as we mix 10 grams of aluminum sulfite with 10 grams of sodium hydroxide, it's very likely that one of those two reactants will get used up first. Once it gets used up, the amount of products that we can make will stop. So the amount of products will be determined by that reactant which ran out. So therefore, it's called the limiting reactant or the limiting reagent. So how do you find it? We know we have 10 grams of one, 10 grams of the other. Which one of those would run out first in this reaction? There's more than one way to do this, but here's the method that I like. I just flip a coin and pick one or the other reactant. In this case, why don't we just start with the 10 grams of aluminum sulfite. And what I'm going to do is set up a string of unit multipliers that will calculate the number of grams of the other ingredient, in this case sodium hydroxide, that I need to react with this, the 10 grams of aluminum sulfite. So I'm asking myself a stoichiometry question that's actually not in the question. I'm asking how many grams of sodium hydroxide do I need to react with this 10 grams of aluminum sulfite? Once I've found that, I'll compare it to what I have. I'll know how much I need, I'll know how much I have, and I can then decide if the sodium hydroxide will run out. So let's jump in. We'll convert the grams of aluminum sulfite to moles of aluminum sulfite. Be sure when you're setting up your unit multipliers you focus on the units like this. Okay, and then we'll switch from moles of aluminum sulfite to moles of the other ingredient, in this case sodium hydroxide. The first multiplier here is just the molar mass of aluminum sulfite. The second one, moles of sodium hydroxide, moles of aluminum sulfite, we'll get these numbers from the coefficients in the balanced equation. And then finally, because this question told us that we had 10 grams of sodium hydroxide, we're going to convert the moles of sodium hydroxide to grams so that we can compare. So first, the molar mass of aluminum sulfite. Grabbing a periodic table, we have 2 times aluminum, 2 times 26.98. We have 3 sulfurs, 3 times 3206. And we have 9 oxygens, so 9 times 16. Adding that all together, I got 294.14 grams as my molar mass. Now the balanced equation up here tells us that 6 moles of NaOH will react with 1 mole of aluminum sulfite. And then finally, the molar mass of sodium hydroxide, Again, with the periodic table, there's 1 sodium, 1 oxygen, 1 hydrogen, and that works out to be 40.00 grams. Again, it's a very good idea to pause the video and try it yourself, and then just check to see if you've got it right. Grabbing a calculator now, 10 grams divided by 294.14, this is going to give me the moles of aluminum sulfite. Multiplying by 6, that will give me moles of sodium hydroxide, and then multiplying by 40, that'll give me grams of sodium hydroxide, and according to my calculations, 8.16 grams of NaOH is the answer to this. Now, what does that mean? Since we began with 10 grams of aluminum sulfite in our unit multipliers, this answer is the number of grams of sodium hydroxide needed to use up all of the aluminum sulfite. Okay, the 10 grams of aluminum sulfite. Now, what can we do with this number? Well, the key now is to compare it to how much we had. So we look back at the question and we notice we had 10 grams of sodium hydroxide, which means we have excess sodium hydroxide. Okay, we only needed 8.16 grams, but we had 10 grams, so we had more than enough sodium hydroxide. The sodium hydroxide then is in excess. It will not run out during the reaction. In fact, there will be leftover sodium hydroxide at the end of the reaction. Therefore, the other ingredient, since we have more than enough sodium hydroxide, we will indeed use up all of the aluminum sulfite. It's going to run out. So aluminum sulfite is limiting. It's the limiting reagent. It's the ingredient that ran out during the reaction and limits the amount of product that we can make. Now, the reason we would want to find the limiting reagent is so that we could answer a question like this in part B. How many grams of sodium sulfite would be produced in this reaction? So we've determined that aluminum sulfite runs out, so we must start this answer with the grams of aluminum sulfite. We're going to ignore the sodium hydroxide because it was in excess. Okay? It does not determine how much we can make. The aluminum sulfite ran out, so it determines how much we can make, so we'll start with it. And now see if you can set up 3 unit multipliers to get your grams of sodium sulfite that would be produced. In the first multiplier, convert your grams of aluminum sulfite to moles of aluminum sulfite. Then convert the moles of aluminum sulfite, and here's your balanced equation now, to moles of sodium sulfite. And then finally the question wanted to know the mass, so we'll convert the moles of sodium sulfite to grams of sodium sulfite. So the first multiplier is again our molar mass, so 1 mole of aluminum sulfite had a mass of 294.14 grams. The second multiplier comes from the balanced equation, and looking at it, we can see that 3 moles of sodium sulfite come from 1 mole of aluminum sulfite. The coefficient was 3 to 1. And then finally, the molar mass of sodium sulfite is 126.04 grams for every mole. Grabbing a calculator, this works out to be 12.9 grams of sodium sulfite will be produced. Okay, so conceptually, be sure you understand that we must start with the limiting reagent that we determined above to determine how much product we can make. because that's what the limiting reagent does. It limits or determines the amount of product. Part C, how many grams of the excess reagent were left over? Well, because of the way we started Part A, this is going to be actually a pretty easy question. We know that we had 10 grams of sodium hydroxide. That's how much we had. And we know that we were only going to use up 8.16 grams. If we look back at Part A, 8.16 grams was needed, so that's what gets used up. So subtract what gets used up from what you had, and the difference is what's left over at the end of the reaction. So 10 minus 8.16 gives me 1.8 grams of sodium hydroxide are left over. You'll notice that I'm trying to obey sig-fig rules. When you end rules for subtracting like this say that the answer must have as few decimal places as the number that had the fewest in the calculation. So since we had 1 decimal place here and 2 decimal places here, we kept only 1 decimal place in this answer. In Part B and A, we were multiplying and dividing, and the rule there is that you keep as many significant digits in your answer as had the fewest in the calculation. So since there were 3 sig figs in 10.0, 4 sig figs in the molar masses, we ended up keeping the smaller number, 3 sig figs, in the answer. The coefficients are never used to round off your answers. They're basically considered to be pure numbers. They have infinite significant digits. So it's not like it might have actually been 3.01 and we rounded it off to 3. It's exactly 3 moles of sodium sulfite for every 1 mole of aluminum sulfite. So ignore the coefficients when rounding off answers to stoichiometry calculations. Part D, how many grams of aluminum hydroxide are produced? Well, again, that's the other product. You have multiple ways to find this now, more than one way to do this. To set it up the same way that we did Part B, we would start with the limiting reagent, 10.0 grams of aluminum sulfite, and with 3 multipliers, we could answer this question. We could find how many grams of aluminum hydroxide are produced. Again, we're starting with the limiting reagent. So we can get rid of the grams of aluminum sulfite. We could switch to moles using its molar mass. Then get rid of the moles of aluminum sulfite and switch to the moles, in this case, of aluminum hydroxide. And finally, it wants the mass, so we'll get rid of moles of aluminum hydroxide and switch to grams of aluminum hydroxide. Using the molar mass again, 1 mole was 294.14 grams. Using the balanced equation here, we can see that 1 mole of aluminum sulfite produces 2 moles of aluminum hydroxide. And then using the molar mass of aluminum hydroxide, 1 mole is 78.01 grams. Grabbing a calculator and keeping 3 significant digits in the answer, we get 5.30 grams of aluminum hydroxide will be produced. Okay, now there was another way to find that answer. Looking back at the equation here, we know that 10 grams of the aluminum sulfite is getting used up. We know that 8.16 grams of sodium hydroxide is getting used up. And in Part B, we determined that 12.9 grams of sodium sulfite would be produced. So now we could use the law of conservation of mass to figure out the mass of aluminum hydroxide that would be produced, we would simply take the mass of the two reactants, 10 plus 18.16 plus 8.16, and subtract the mass of the one reactant that we already know, 12.9, and we get 5.3 grams of aluminum hydroxide would be produced. That's because that method worked because we knew everything else in the equation. Therefore, the law of conservation of mass would have let us find the remaining substance in the equation. Okay? So there's two different ways to answer part D. We'll do one other question here together. So let's skip over to question number 4 on the worksheet. Question number 4 is a little bit tougher. Not much, but a little bit. It says, first of all, to write the balanced equation for the reaction of lead 2 nitrate and sodium iodide. It sort of spoon feeds us a bit by telling us what the products are. You should be able to figure out the products by classifying the reaction. When you hear lead 2 nitrate, you know that that means lead 2 plus bonded to NO3 minus, and sodium iodide you know is Na plus bonded to I minus. And now you realize that that's just a double replacement reaction, and they're going to just trade partners. So lead is going to bond with iodide, and sodium is going to bond with nitrate. The positives go with the negatives, right? And so the reaction would have been Pb, and because lead is 2 plus and nitrate's only 1 minus, we need 2 nitrates reacting with sodium iodide, plus 1 and minus 1, so 1 of each, produces, and when they trade partners, lead, which is 2 plus, bonds with I minus to give me PbI2, and then sodium, which is positive, bonds with nitrate, which is negative, to give me NaNO3. Now, balancing this equation, we see 2 nitrates on the left, so if we put a 2 in front of sodium nitrate, that gives me 2 nitrates on the right. That 2 gives me 2 sodiums on the right, so putting a 2 in front of NaI fixes that. This 2 gives me 2 iodides, but we wanted 2 iodides, so we're good. And that means there's got to be 1 lead, and indeed there was 1 lead on the left. So that equation is now a balanced double replacement reaction. So it says, if we start with 25 grams of lead nitrate and 15 grams of sodium iodide, how many grams of the sodium nitrate could form? Okay. Well, let's pick one of the 2 reactants again. I'll take the first one just out of habit. You have 25.0 grams of PbNO3 lead nitrate. And what I'm going to do is set up some unit multipliers. In my head, I know there's going to be 3 because I'm already anticipating what I'm going to do. I'm going to find how many grams of sodium iodide I needed. So the first multiplier goes from grams to moles of lead nitrate. The second goes from moles of lead nitrate to moles of sodium iodide. And the third one from moles of sodium iodide to grams of sodium iodide. The first and the last are molar masses. The molar mass of lead nitrate is 1 mole 331.22 grams. Looking at our balanced equation, 2 moles of NaI will react with 1 mole of lead nitrate. And finally, the molar mass of sodium iodide, 149.9 grams per each mole. Grabbing a calculator, this works out to be 22.5 grams of sodium iodide. And what does this mean? This many grams of sodium iodide are needed to use up all the lead nitrate. But look back at the question. How much sodium iodide did we have? Well, the question said we only had 15 grams, but we need 22.5 to use up all the lead nitrate. Therefore, what's the conclusion? If we need more than we have, then in this question, the sodium iodide is limiting. It's going to run out. We don't have enough. It's the limiting reagent. And the other ingredient, the lead nitrate in this question, would be in excess. It's going to be left over at the end of the reaction. So now that I know the limiting reagent, we can answer the question, how many grams of sodium nitrate could form? We'll start with the limiting reagent, 22.5 grams of, we didn't have 22.5 grams. We had 15.0 grams in the question, right, of sodium nitrate. And set up some multipliers to find out how many grams of sodium nitrate we could form. And I just realized I'm making a few mistakes here. That was sodium iodide there. So we're going to get rid of the grams of sodium iodide and switch to moles of sodium iodide, and then moles of sodium iodide to moles of sodium nitrate. Now I've got it. And then moles of sodium nitrate to grams of sodium nitrate. So the first one is a molar mass. 1 mole is 149.9 grams for sodium iodide. The second one is moles of one substance to moles of another substance. That would come from a balanced equation. So we look up and we see 2 moles of sodium nitrate for every 2 moles of sodium iodide. And then finally, the molar mass of sodium nitrate. 1 mole is 85.00 grams. Grabbing a calculator, it works out to be 8.51 grams of sodium nitrate will form. So we were having to write a balanced equation ourselves here and then use it to answer the stoichiometry question below. So we found which ingredient was limiting, and then we used the limiting reagent to figure out how much product we could make. There's 2 straightforward, typical limiting reagent problems.